Hey guys, welcome to day 11. The topic today is basically accuracy, precision, and error. All right, accuracy is pretty easy to explain. It's how close something comes to like its true value, okay? So the simplest example would be is if I were to give you a bullseye. Uh, we can all agree that the accepted value would be the center of the bullseye. So if you can hit the center of that bullseye, then we say that you are accurate. Now, we can also use accuracy to describe numbers. So let's say we have a number, and let's say our value for pi. We know that the accepted value for pi is 3.14159, and pi represents the the diameter to the circumference of a circle. Now, let's say experimentally we come up with the value of 3.37. We realize that we're close, but we've kind of missed the mark a little bit. So the accepted value is 3.14, and experimentally we maybe measured and calculated the value for pi in a lab, and that value was close, but maybe a little bit off its mark. So, we can describe accuracy a couple of different ways, and one of those ways is going to be error. Now, precision is a little bit harder to explain. Okay, precision can mean a couple of different things. Today we're going to kind of focus on maybe the bullseye definition of precision, and tomorrow we're going to focus more on what is the numerical value of precision. So, precision is basically how closely are those answers grouped together. So, if we're shooting at a bullseye, and okay, we missed the bullseye, so our accuracy, it's not great, it's not awful, but we have accuracy problems. But what you see here in this example is that all of our shots are very closely grouped together, and that is an indication that we do have a certain degree of precision. Accuracy might be a little bit off, but precision is decent in this example. Now, ultimately, we would like both accuracy and precision, and this bullseye shows both. We can look at something like this where, if you were to take the average of these 8 shots, the average of those 8 shots might land somewhere in the pink region and say, only 3 of those 8 shots actually hit the bullseye. But if you take the average, that's not really that bad. Whereas, what we're trying to avoid is both missing accuracy and lack of precision. So this one over here, like, okay, one of our arrows hit the bullseye, but they're not very tightly grouped together. None of them really hit the mark. Well, I guess one did. So this one shows neither really accuracy nor precision. Ultimately, we would like both accuracy and precision. Now, there's another way we can describe precision. It's a little bit more complicated. Let's say we have a digital scale. And the digital scale at home measures things to the nearest gram. So I could measure, maybe something weighs 1 gram, okay? And this is my home scale, and maybe I paid $10 for this scale. So then I go in and I say, Miss Mead, I need to weigh this thing. And Miss Mead has some scales, and you throw it on that scale, and it says, well, it's 0.9 grams, okay? So Mrs. Mead has some scales, and these scales are a little bit more precise. So your home scale only goes to the nearest gram, but Miss Mead has a scale that goes to the tenth of a gram, and maybe the scale costs $100. But then you realize you want a more specific answer, so you go see Mr. Burkhart, and he's got a scale in his room, and it goes to 2 decimal places. So Mr. Burkhart's scale is the most precise and is probably also the most expensive. I think our scales cost about $250 a piece. So in the case of measurements, precision is the number of decimals or the degree to which your answer is given. A home scale might go to the nearest 1 gram. Mrs. Mead's scale goes to the tenth of a gram. Mr. Burkhart's goes to the hundredth of a gram. There are scales that go to the thousandth or even 10,000th of a gram, and those are extremely expensive. So precision can be talked about grouping of shots fired at a bullseye, or precision can also be used to describe the range of digits or the number of digits given in a particular value, okay? All right, so let's move on a little bit. Accepted value. This is Well, the right answer. So, if you look for the accepted value of pi, the accepted value is 3.14159. And it's a correct value based on a reliable source. And that reliable source could be your textbook, it could be the internet. If you are using the internet, sometimes just say maybe you should check 2 or 3 different sources. But chances are, if you use the internet, they're relatively close. Now, we know that pi can go on for hundreds and hundreds of decimals. In fact, I think it just goes on forever, but this is a relatively precise answer. So 3.14159 is the accepted value, but many times in your math classes, you maybe only use 3.14. So they're both accurate and that they both represent the true value of pi, but this one would be more precise, and the one that you kind of memorize, the 3.14, would be less precise. Both of them are correct, just one of them has more digits and therefore is more precise. So accepted value is the correct value based on a reliable source. I could go so far as to say that, hey, today is Thursday, and if you're doing this lesson when you should be, it's probably Thursday, April 9th. That is a fact. Now, experimental value. This is what is measured in the lab. Sometimes it's called the observed value. Sometimes it's called the accepted value. Regardless of what you call it, it is what you determine to be the value as measured or calculated in the lab, okay? So oftentimes your experimental value deviates from the true value, and that's okay. So what we're going to do is we're going to use error to describe that. Now, there's 2 basic kinds of error. The first type is just called regular error. Sometimes I even call this absolute error. But realize that it is the experimental value that you determined in the lab minus the true value that you looked up in a reliable source. This number can be positive or it could be negative, and it should include units. Now, percent error, on the other hand, is never going to include a positive or negative sign. And if you look a little bit closer, you'll realize that we use these little absolute value symbols. So even if we have a negative value for error, when we look at the absolute value of that, we really just kind of drop that negative sign and just look at the absolute value that it is. So the percent error is your absolute error or regular error divided by the true value, and then we're going to take that and we're going to multiply it by 100%. Okay. Now down below, this is the worksheet that I would be giving you if it was a normal school day. So whether you do it or not, that's up to you. Just make sure you do complete the Google form for your points for today. But it kind of just gives you an idea of the types of questions I'm going to ask you. All right, so we've got examples of bullseyes. You can look up above and you can say which one's accurate, which one's precise, which one's neither, which one is both, okay? Now, one of the things that you are going to have to do is you're going to have to calculate some error in the homework assignment. So what I'm going to do with you is I'm going to do one example with you. I'm going to do example number 12, and then hopefully that'll be enough to kind of get you to where you can do the example in the homework by yourself. All right. In a lab, you are given a block of aluminum. You measure the dimensions of the block, and you measure its volume, and you calculate the density to be 2.68 grams per centimeter cubed. This is going to be your experimental value. Okay. Then you go on and you look up the true value of it. You look it up in a textbook or you look it online, and the true value is is going to be 2.7. So what I want you to do for this problem is I want you to calculate error, and I want you to calculate percent error, sometimes called relative error. So let's do that together. All right, so I've kind of already set the problem up. I know it says write your equations down up above, and we already kind of set it, but your experimental value is going to be 2.68. Don't forget units. And the units in this case is going to be a gram per centimeter cubed. And then our true value, as determined by our word problem, was 2.70. And you have to be careful about how I word things. Just read it again, and usually I'll give you some clues as to which one's the experimental and which one's the accepted value. So when you subtract units, they have to be the same. So if I said 5 bananas minus 3 bananas, your answer would be 2 bananas. So in our case, we have grams per centimeter cubed minus grams per centimeter cubed. Our unit is going to remain. Now, when I plug this into my calculator, I actually get a negative value. my calculator gives me negative 0.02, and in order to be correct, you have to include the correct unit. Just remember, a centimeter cubed minus a centimeter, or gram per centimeter cubed minus a gram per centimeter cubed gives you a gram per centimeter cubed, okay? So that would be my final answer for error. Now I move down here and I want to do relative error or percent error, okay? Now, basically, the top of this equation is kind of what we did up here. So rather than show my work again, I'm just going to take my previous answer, which is negative 0.02 grams per centimeter cubed. And remember, when you're dealing with absolute values, you can just kind of drop that negative symbol. So it's just going to be 0.02. And then we're going to take and we're going to divide that by the true value. And the true value was 2.70. And the unit would be a gram per centimeter cubed. Okay. So when I do this, I get my calculator out, I plug it in. This is what my calculator gives me. I already did it. And my calculator gives me 0.00740 decimal. Okay? Now, guys, a negative divided by a positive is going to be negative, but since we're dealing with absolute values, I'm giving you permission just to drop that negative symbol. Now, what you might have noticed is that I forgot to do something. I forgot to multiply that by 100%. So when I do that in my calculator, I get 0.74, and a gram per centimeter cubed divided by a gram per centimeter cubed is going to cancel out, and what you're going to end up with is no unit, but what you're going to do is you're going to plug in just percent, okay? So, final answer for that particular problem, just remember for percent error, you cannot have a negative number. For just regular old error, you can have a negative number. The example that I gave you in your homework is very similar to one of the examples in the problem up above. So remember, if you guys have any questions, feel free to leave a comment on Google Classroom, or you can email me directly. Guys, I miss you. I love you. Hope to see you before the end of the year. I'll talk to you.